Hello, everyone, and welcome to the first live session of our webinar series, Design of Facade Attachments, presented by Alex Zimmer and James Parker. Today is May 9th, 2019. My name is Nate Goner with AISC, and I will be your moderator for this webinar series. I would like to introduce today's speaker, Alex Zimmer. Alex Zimmer is a senior project manager at Simpson, Gumpertz & Hager's Waltham, Massachusetts office. He joined SGH's structural design group in 1998. He designs new building structures with a focus on new academic and healthcare buildings. He also investigates and rehabilitates existing buildings and other structures. Mr. Zimmer earned his Bachelor of Science degree in Engineering from Swarthmore College and his Master of Science degree in Structural Engineering from Stanford University. He is a member of the American Society of Civil Engineers, American Concrete Institute, and the American Institute of Steel Construction. Alec worked with SGH Senior Principal James Parker to develop AISC's Design Guide 22 on facade attachments to steel frame buildings, and he's presented a seminar on this topic for AISC and cities around the U.S. Alec, thanks very much for being here today, and I'll now turn the floor over to you.
Thank you, Nate. Thank you for that introduction. My name is Alex Zimmer. I'm with Simpson, Gumpertz & Hager in Waltham, Massachusetts, and today we'll be talking about facade attachments to steel frame buildings. As part of this seminar series, there's a pre-recorded webinar that covers fundamentals of facade attachments, design criteria, design and execution responsibilities, thermal bridging, and planning for clearances and accommodating tolerances. We won't spend much time on that today. Instead, we're going to focus today on a number of different facade types. We're going to focus on traditional masonry cavity wall systems, panelized facade systems, aluminum glass curtain wall systems, and toward the end of the presentation we'll be talking about sizing joints to accommodate vertical movements. A week from today, in the second session, we'll be covering things like designing of spandrel beams and floor slab edges. So today we'll be talking about masonry curtain walls. Let's dive right in. We'll be talking about strategies for supporting masonry cavity wall systems and decisions for horizontal joint movements, etc. So in cross-section, here's a general view of a masonry cavity wall system. We're showing it generically here as brick, but it could also be traditional laid stone on mortar beds. And here I should mention that we are specifically talking about hand-laid masonry. We're not talking about thin brick that is set on metal pans that might be attached to a backup system, and we're not talking about thin stone veneer on a rail system. We're talking about mason-laid masonry. And so working from outside to inside, there's a masonry veneer. There are some lateral ties here shown as number 2 that connect that masonry veneer to a backup structure, which here is shown as number 8. Shown generically here is steel stud backup, but it could also be a concrete masonry unit backup system. Behind the masonry veneer, there's an air cavity and then an insulation layer. And behind that, there is a waterproofing barrier, which is lapped into some through-wall flashing, which you see here, which daylights out here at number 10. And beneath the shelf angle, there is a soft joint, which is designed to accommodate vertical movement of the veneer system relative to the building structure. I should add here that this is not a barrier wall system. That is, it's expected that there will be some moisture that gets behind the masonry veneer and that the waterproofing and the flashing direct that moisture back to the outside of the building. So it's not intended that the masonry itself be watertight. The waterproofing barrier is behind the masonry, as you see back here. Here's some components of that masonry cavity wall system. In the top left, you see some mortar nets, which are designed to allow free drainage of the cavity behind the masonry veneer. And those allow drainage in case of mortar droppings, as you see in the upper right. Mortar that gets dropped down into the cavity as the masonry is being assembled. You also see a masonry veneer tie here in the lower left. This takes lateral loads on the masonry veneer and transmits it to the backup structure behind. And here you see some of those masonry veneer anchors installed in a wall through the insulation layer. And here you see the cavity and the brick veneer itself. Now, proper design of any masonry veneer includes consideration of movement joints. All masonry grows with changes in ambient temperature, and brick veneer in particular changes volume as it absorbs moisture from the environment. And that moisture growth in brick veneer in particular is irreversible. So the facade needs to be jointed to accommodate volume changes of the brick and structural movements, lest the facade end up looking like one of these lovely facades with the sealant joints bulging out or cracking in the veneer itself. Now, the pattern of the joints is something that typically the architect on the project is going to have control over. The brick veneer or masonry veneer is panelized to accommodate movements in the brick, to accommodate those volume changes I was just talking about, and also to accommodate movements of the building structure behind the masonry veneer. Vertical control joints are usually located at window jambs, as we show here, and also near building corners, as we show here. There's also horizontal soft joints, typically located at every floor. In this case, they're located at the window head. It's also possible to locate those horizontal soft joints closer to the floor line, but if you do that, be aware that you need to provide a loose lintel that goes over the head of punched window openings. As I said, the architect usually will decide where these joints are located and where the shelf angles are located and how those joints are to be sealed, but the structural engineer of record can, however, help the design team by providing information about how much the building structure is likely to deflect when it's in service. So there are a number of fenestration strategies. One is for punched window openings, as you see here, individual window openings with masonry between them. And there's a shelf angle at the window head, as you see here, lined in red. And just below that shelf angle, there's a soft joint that accommodates the volume change of the brick and allows the building structure to deflect behind it. Another fenestration solution is a strip window, so a continuous horizontal strip of windows. And again, in this case, the shelf angle is hung from a spandrel beam, as you see here. You've got some hangers and a shelf angle here, and that shelf angle is continuous, and that must be at the window head in the case of a strip window. And that's starting to get into some of the parameters that really affect the design of the masonry cavity wall system. There are a number of architectural decisions, dealing with fenestration and joint patterns. There's some dimensional things that we need to consider, particularly the story height and how much masonry is supported on each shelf angle. And that in turn influences the magnitudes of the loads that we need to design for. We need to be able to accommodate adjustability in the field when the building frame and the shelf angles are being set. We need to accommodate durability and be sure that we have a nice durable system for supporting the veneer, since these connections are likely to be concealed for the life of the building. And we need to make sure that we are accommodating the thermal performance objectives for the project. So let's dig into some of the architectural objectives first. One has to do with the location of the shelf angle. In this graphic, you see it hung well below the floor level on a hanger with a shelf angle down here. And to accommodate the twist on the spandrel beam, which we'll start talking about later on today, we have a kicker angle that braces the rotation of that spandrel beam back to the underside of the slab adjacent to it. But be aware that if you take an approach like this, that you may have mechanical distribution or ductwork running very close to the spandrel beam that would be impeded by this angle. Another thing to watch out for is roller shades on the inside of the window right here, and the hanger angle assembly needs to be able to accommodate those roller shades. Vertical joints are also an important consideration, and as I mentioned, the architect will typically set the location of those vertical control joints. The locations of the control joints depend upon the material properties of the cladding and where the locations of the openings are in the facade, and they typically will be located near corners, typically near window jambs, but you may need to have a break in the vertical control joint in the masonry veneer itself to accommodate volume changes. Generally, it's a good idea to break the relieving angle wherever you have a change in relieving angle elevation and have a vertical control joint there. It's okay to put a vertical control joint between hangers, so in other words, in the mid-span of the shelf angle as we show in A, but generally we try to align those vertical control joints with breaks in the relieving angle itself. Now, in terms of the dimensions of the relieving angle or shelf angle, typically that's going to be governed by the cavity of the behind the masonry veneer and the masonry veneer itself. Typically, we want 2/3 of the masonry veneer bearing on the shelf angle. That's to keep the resultant of the masonry veneer kern located over the shelf angle, to minimize the chance that it's going to roll away from the shelf angle. Behind that, you see the cavity and the insulation layer and the exterior sheathing. Now, in modern energy codes are tending to require thicker layers of insulation and moving away from foam plastic insulations toward mineral wool insulation, and those changes have made the gap between the backup structure and the hangers for the shelf angle a bit wider than they used to be in previous years. So the masonry is getting pushed further and further away from the hanger system, which leads to longer horizontal shelf angle legs. And for that reason, it may be tempting to want to use a bent plate here instead of a hot-rolled shelf angle. I would recommend trying to stick to a hot-rolled angle because it has less variability than a bent plate does in the position of the horizontal leg. And so to get around that, it may be advantageous to provide shims behind the horizontal shelf angle's vertical leg, or provide fins that stick through the insulation layer to reduce the horizontal leg of the shelf angle. We also need to think about the location of the backup wall, how thick that backup wall is, and its relationship to the spandrel beam and the columns along the building's perimeter. We're showing this typically here as CMU, but it could just as easily be a cold-formed steel stud. It's usually not in the structural engineer's scope of services to design the backup wall. Usually it's performance specified by the architect. However, it's been my experience that at some point in the project, the architect will ask for guidance on specifying the thickness of the backup wall, because he or she needs to know if the anticipated wall works for the wind loads and the seismic loads. And as I said, it's not usually in our scope of services, but I'm happy to help provide that guidance because it sets the location of the slab edge with respect to the spandrel beam. And I need to know that as the structural engineer to design my slab edge and to design the elements that support the backup wall and support the masonry veneer. We also need to make sure that the slab edge is adjustable in the field. And we'll talk more about slab edges in upcoming presentations, but be aware that you need to be able to adjust that slab edge's location in plan relative to the spandrel beam in the field, because the spandrel beam may have some natural sweep to it. The columns may not be perfectly on the column center lines, and we need to make sure that we're not posing some limitations on where the veneer and backup wall can be. Now we'll talk more about designing for vertical movements toward the end of this presentation today, but there are some things that are specific to masonry veneer systems that I want to mention here. First is there's spandrel beam deflection. Spandrel beams will deflect vertically between the columns, as they will in any facade system. In addition, the spandrel beam is going to rotate due to the eccentricity between the masonry veneer and the spandrel beam. And it's going to rotate as a rigid body around a point at the center of the top flange. And so that rotation of the spandrel beam is going to induce a vertical displacement of the shelf angle tip as well as a horizontal translation of the shelf angle tip. And we need to keep those movements due to rigid body rotation of the spandrel beam in mind. In addition, the shelf angle is going to rotate between the hangers that support it, as you see here, and it's going to deflect in flexural bending. So we need to calculate what those shelf angle rotations and deflections are. In addition, the brick, which is beneath the shelf angle, is going to experience moisture growth over its lifetime, and it's going to change volume with changes in ambient temperature. And we need to keep all of those in mind when we design the soft joints or sealant joints that are below the shelf angles. A quick word here on joint compressibility, and again, we'll talk more about this at the end of today's presentation. Most joint filler materials, which you see here is this yellow shaded area, have a compressibility or extensibility of about 30% of the original joint size, or the original undeformed joint size. Some sealant joints can compress up to about 50%, but this is something over which the architect typically has control through specifications, and that's something that we as the structural engineers need to be cognizant of. We also need to think about in-plane movement. Typically, a masonry cavity wall system is going to displace as a rigid body for in-plane motions, and that is to say the panel of brick, which we've shown here in this orange color, is going to displace with the lower floor, and the floor above is going to slide relative to it through that horizontal sealant joint at the top of the masonry panel. For out-of-plane motion, the exterior wall acts like a simply supported beam, flexing and rotating about pins at the shelf angle as well as at the top of the panel. Back to in-plane movements for just a second. Understanding how the backup wall system runs by the columns along the perimeter of the building is very important. Columns can be a pinch point, and you may need to reduce the thickness of the backup wall, as shown here in the lower image, to allow the column to displace laterally for in-plane wind and seismic movements. If we don't do something like this, or allow the masonry to run, the backup system, to run by uninterrupted, the column can bind up on the backup wall and impose lateral forces into the backup wall for which it wasn't originally designed. Let's talk about some top-of-wall connections. Typically, the architect will perform and specify how the top of the backup wall is connected to the base building structure, but as the structural engineer, we need to be aware of how that backup wall is laterally restrained. Now, in the image on the left, we're showing a CMU wall. This could just as easily be metal stud, and here you see it laterally restrained with this connector back to the spandrel beam. This connector restrains out-of-plane motion in the left to right direction on the screen, but it allows the wall to slide independently in the direction perpendicular to the plate of the screen. So we're not restraining the displacement of this upper floor to this backup wall. Another solution where the backup wall does not run completely by the spandrel is to provide some clips at the bottom flange of the spandrel and a short portion of infill within the depth of the spandrel beam, as you see here. On the right, you see an image of a metal stud backup wall. This is from one of my recent projects. And here we've provided a plate, which you can barely see right here where my green arrow is. And at the underside of that plate, the studs from the floor below come up to that plate and have a deflection track at the underside of that plate. And then above that plate, there will be infill studs between the top of the plate and the underside of the slab above. And generally, you want to try to have the masonry system, the cavity masonry veneer system, have a horizontal joint at the same location as the backup wall, so that you're not imposing differential vertical movement between the two. Let's talk about durability for just a moment here. As I mentioned before, the assumption is that a masonry cavity wall is not a barrier wall system. It doesn't prevent moisture from getting into the building. What does prevent the moisture from getting into the building is this waterproofing membrane applied either as a liquid or a sheet good over the exterior face of the backup wall. And that gets lapped into some metal flashing, which I'm showing here, and which daylights to the exterior of the building. Now that metal flashing comes in sheets and strips which have to get joined together in the field, and it's possible those joints could leak over time. And if water makes it past those joints in the metal flashing, it can accumulate on the horizontal leg of the shelf angle and cause a corrosion and durability problem over time that would go undetected until there's a real problem. And so for that reason, we always galvanize our shelf angles. And in some projects, we've actually taken to using stainless steel shelf angles in part to help mitigate thermal bridging as well. Now, there are two papers that we reference for design of shelf angles in Facade Design Guide number 22. One is by Grimm and Ura, and the second by Tide and Krogstad. We find that the paper by Tide and Krogstad imposes fewer limitations on the designer, and we prefer it for that reason. And so in Design Guide 22, there are a number of tables based on Tide and Krogstad's paper that look like this. So to run through what these tables do quickly, they provide a certain vertical height of brick that gets supported by a shelf angle, a spacing of the connection of the shelf angle to hangers or to the base building structure, so at 24 inches on center or up to 6 feet on center, and a variety of horizontal and vertical shelf angle legs and thicknesses. And for a given shelf angle size and thickness and a given spacing, this determines the amount of vertical deflection at the tip of the shelf angle between the hangers due to rotation and flexure. So this is a very handy table to have when you're trying to determine how big your sealant joint below the shelf angle should be. So here's a section through a spandrel beam showing a masonry veneer with shelf angle and hangers. A fairly modest hanger hung below the slab here with a kicker to restrain rotation of the spandrel beam. Here you see one of my recent projects where the hangers haven't yet been plumbed and the shelf angles haven't yet been set, but it's a similar concept. There's a bracket or gusset that's welded to the spandrel beam web and a hanger angle that extends down from that and supports the shelf angle. Excuse me. And throughout today's presentation, I'll include a number of slides like this which have key notes to the previous slide. I won't take the time to read through those today, but they're here for your convenience. So let's dig into a slightly more detailed view here. We have the spandrel beam and the slab, and we're not calling a particular orientation of the slab on deck in this case. And the masonry veneer on the outside, about 2/3 of which bears on the shelf angle. And that shelf angle is connected to a hanger, which you see here. In this case, it's a 5 by 5 by 3/8 angle, spaced at 4 feet on center. During erection, the shelf angle is bolted to the hanger angle. And once the final location of the hanger angle and the shelf angle is set in the field using erection bolts, the shelf angle is welded to the hanger angle, and that weld is touched up with zinc-rich coating because we always galvanize the shelf angle itself, and the welding process burns off the galvanizing if it wasn't masked to begin with. And we also field weld the hanger angle to the gusset plate in the spandrel beam. As I've mentioned, we have a fairly significant eccentricity between the masonry veneer and the center line of the spandrel beam. So not only does that cause vertical deflection, but it causes rotation of the spandrel beam due to the eccentric load of the veneer. Excuse me. And to restrain that rotation, in this example, we're providing a double 3 by 3 by quarter kicker that restrains the rotation of the spandrel beam. We also tend to use what I call roll beams in this position. That could be a floor beam if the deck is perpendicular to the plane of the page, or it could be a relatively small beam like a W10 or a W12 that is perpendicular to the spandrel beam. And that can also be used to restrain the rotation of the spandrel beam. Here's an example of a detail from one of my recent projects where we incorporated a thermal isolation pad into the shelf angle and hanger assembly. So this is very similar to the detail I just showed. It's just opposite hand with the gusset plate in the spandrel beam web, the vertical hanger angle, and here we've introduced a thermal isolation pad that is in the plane of the insulation in the cavity. So in this case, we had metal stud backup, and that was in this plane with a plate here to support the studs, hanger angle, and the thermal isolation pad. And the relieving angle assembly is attached to the hanger angle with threaded studs. So let's take a look at the blow-up of that detail. Here we have threaded studs that are shop welded to the hanger angle. The thermal isolation pad is placed over that, and this assembly is field erected over that. One thing to be aware of here is that if you do a connection like this, be aware that the threaded studs are not only in shear, but they're also in flexure through the thickness of the thermal isolation pad and the thickness of the horizontal outstanding leg of this angle here. We need to think about what happens not just in the field of the wall, but at the corners of the building. So here's an example of an interior or reentrant corner we need to think about where we locate those hangers and shelf angle supports with respect to the reentrant corner columns. And similarly, we need to think about what happens at exterior corners. In the case of the project on the right, we had shelf angle hangers that were coming off the spandrel beam, but we also had some hangers coming directly off of the column. And even in the field of the wall, we need to think about where the vertical control joints are and whether it makes sense to attach the shelf angle directly to the column, or whether the shelf angle should cantilever beyond the last hanger adjacent to the column. In the case of long hangers, there are a number of challenges that that we need to pay close attention to, particularly for out-of-plane loads. In the next slide, you'll see again those keynotes for the previous slide. But let's back up here just one second. So with a long hanger, you can develop a lot of rotation through the hanger itself in flexure, and that can put some fairly severe deflections in the tip of the shelf angle that we need to account for, and may drive the width of the soft joint below the shelf angle. So there's some things we need to consider here, one of which is where the idealized hinge in the connection between the hanger and the spandrel beam is. Is the idealized hinge in the connection between the hanger and the gusset plate, or is the idealized hinge between the gusset plate and the web and flanges of the spandrel beam? I would argue that this detail on the left, where the hinge is between the hanger and the gusset, is probably a more realistic assumption of where the hinge is, since the connection between the gusset and the spandrel beam web and flanges is likely to be quite rigid because it will be welded. So looking at the deformed shape of the hanger and shelf angle and kicker assembly, we have a pin here at the top of the hanger, and we need to assume that the shelf angle itself is going to try to rotate, and we need to restrain that rotation. We can do that through bending of the hanger itself, assuming the kicker is a pin connected or truss member, or we can allow the kicker to hanger assembly to be moment connected, and that will tend to reduce the rotation of the shelf angle. But be aware that if you do that, you have to design the kicker not just for axial compression and tension, but you have to design it for the moment due to the dead load of the masonry veneer. Some other concepts for long hangers are to provide a girt of some sort just above the shelf angle. In this case, we're showing an HSS section. You could also do it with a channel section, as we show here in the next slide. And the objective here is that channel or girt, or HSS, whatever section you choose, would span horizontally between hangers, or perhaps maybe even span horizontally between columns. Be aware that if you do something like this and you're not designing the girt for the vertical load of the masonry as you would in this channel, for example, the channel is not very stiff for weak axis bending, that the hanger in this case would still need to be designed to accommodate the vertical load of the shelf angle, and that would still impose a twist on the spandrel beam that you need to deal with either through designing the spandrel beam for torsion or restraining that torsion through kickers or roll beams. Now, in all the cases we've looked at so far, we've looked at a case where the backup wall runs to the underside of the slab. It is sometimes advantageous, particularly when you have strip windows or a parapet condition, to run the backup wall directly by the slab edge. So in other words, using a shorter slab edge and running the backup wall past. If you do this, you need to be aware that you have to restrain the backup wall laterally on the slab, whether through an angle as we're showing here, or perhaps through a connection to the face of the slab, in which case maybe you need to use a bent plate rather than a light gauge pour stop to attach the backup framing to the slab edge. Another thing to consider here is that you need to plan for a gap between the slab edge and the interior face of the backup wall. That's to accommodate tolerances in the field, and that is also to allow the tolerances of the backup wall to be adjusted as well. That said, that gap does need to be filled once the backup wall is in place with some fire safing to prevent hot gases and flames, if there's a fire in the lower floor, from migrating through this gap into the upper story of the building. Again, here are the keynotes to that previous slide. It's also possible to support the shelf angle directly from the slab edge. And this is an efficient way to do it if you need a robust slab edge for other reasons. For example, if you have a masonry backup system where you have to design a fairly robust slab edge, it may be advantageous to have the slab edge do double duty, support both the backup wall and the masonry veneer. That means that the slab itself has to be designed for both flexure and shear, and that you have to consider the fact there's negative bending in the slab and design the slab reinforcement for negative bending with negative moment well back into the building itself, beyond the perimeter beam. There are some disadvantages to doing this. It can limit the amount of adjustability in the field. Typically, the slab edge is going to be set by the steel erector, and the slab is going to be poured long before the masonry veneer gets installed on the building. And once that slab edge is set, there are few ways to adjust in and out of the plane of the page where that shelf angle is. You may have to plan on installing shims between the shelf angle and the bent plate pour stop that we show here. Here's another example of this very condition where we've supported the masonry veneer directly from the slab edge, and we've incorporated a thermal isolation pad in between the shelf angle assembly and the bent plate pour stop. And I'll blow that up so you can see it here. And as you can see, we've provided a welded bar coupler on the vertical leg of the bent plate with bars developed back into the slab to take the negative bending associated with the masonry veneer in the backup. Again, here are the notes to that previous slide. So there are a number of potential challenges that we need to think about when we design masonry veneers and supportive masonry veneers. We need to make sure we provide adequate adjustability for adjusting where that shelf angle is. We need to make sure that at least 2/3 of the masonry bears on the shelf angle, and if we don't provide adequate adjustability, we may need to add an extension to the shelf angle in the field if it's been set improperly. We need also to make sure that we are accommodating of the through-wall flashing that ties into the backup waterproofing, and make sure that can get daylighted to the outside of the building. We also need to make sure that we have an adequate sealant joint size, and that sealant joint that's below the shelf angle is sized for thermal movement and masonry growth due to moisture as well as the thermal movements. We also need to make sure that that joint is sized to accommodate the spandrel beam deflections that occur after the masonry is in place and the sealant joint is sealed. We also need to think about what happens at the corners in atypical conditions, things that may not be well documented in our design. So you need to think about not just what's happening in the field of the wall, but around the corners of the building as well. That concludes the portion on masonry cavity walls. Let's move on to talking about panelized facade systems. There are a number of different panelized facade systems, and the principles for supporting them are generally the same, regardless of what type of panelized facade system it is. You can have things like exterior insulation finish system erected over steel studs, which are panelized in a shop and brought to the site. You can have panelized thin brick on metal studs, such as this. These were assembled off-site and lifted onto the building. You can also have glass fiber composite panels. This is an addition to an older building which had masonry walls below it, but this is glass fiber composite above. You can have a thin stone veneer set on rails that's panelized and brought to the site, or even most traditionally, we can have precast panels, which are essentially a veneer on the building. In this case, these were panels that were supported from a shelf on the foundation and laterally attached to each of the floors of the building. So in general, in cross-section, you have essentially two different types of connections. You have a dead load connection, which takes the dead load of the panel, and you have a lateral or tie-back connection that takes only lateral forces on the panel and allows the structure to displace with respect to the panel. Now, these don't necessarily have to be at the bottom and top of the panel. Sometimes panels are hung. Sometimes panels are supported on the foundation. But these are the fundamental types of connections. And I'm showing precast here, but these could just as easily be any of the other systems I just talked about in the previous slide. So some strategies for supporting panels. I think perhaps the most important aspect of designing for support of panelized facade systems is that the gravity load really should be supported only at 2 points for each panel. This ensures that the distribution of the gravity loads in the panels and at the bearing supports is statically determinate. If we support it for gravity load at multiple points, we get an indeterminate system, and it's nearly impossible to determine the actual distribution of loads in the panel once the panel is erected on the building. And I say it's nearly impossible to determine that because it may be necessary to shim these connections to get the panels plumbed and squared. In the case of the panel I'm showing on the left, I'm showing that this panel is restrained from both vertical and horizontal motion in plane at the left-hand corner, but only vertical movement on the lower right-hand corner. And that's to allow the panel to change with changes in temperature with respect to the base building structure behind it. At all 4 corners, you see an X. And in that diagram, this means that we're restraining out-of-plane load at all those 4 corners. Now, this panel is supported at the bottom for gravity loads, but it's also possible to hang a panel from the top, and that's what we're showing here with the gravity supports in the upper left and upper right corners. And we're resisting in-plane forces through this connection in the middle. And at all 6 points, we're resisting out-of-plane loads. Here's the view of the back of a panel. We're showing a thin material over a metal stud truss, but this could just as easily be a precast panel. And what's important to see here is that we have 2 gravity load clips on this particular panel and 2 tieback points. Again, you really only want 2 gravity supports, and you can have multiple lateral out-of-plane clips. So let's talk about some of the factors that affect the design of the cladding panels, how they're panelized, and where the connections on the building go. As a structural engineer of record, we're not responsible for a lot of the things that I'm going to talk about here with respect to the architectural features of the building, but we need to be cognizant of them. So we'll talk about architectural layout, we'll talk about relative movements, we'll talk about magnitudes of lateral loads and how to accommodate those. We'll talk about some field adjustability, and we'll focus a little bit on durability of the connections. In terms of durability, let's start with the last one first. It's important to realize that most panelized facade systems are what I'd call a barrier wall system. They rely on the panel and the sealant joints or gasket joints between those panels for water tightness to prevent moisture from entering the building. And so the whole system really depends for durability purposes on those sealant joints. Let's talk about layout of panels or panelization, typically going to be governed by the architect, but also influenced by what the manufacturer can ship to the site and what the manufacturer can erect, and the economics of doing a variety of different kinds of panels. Aesthetics often govern the size of the panels, as do the joint patterns between the panels. For example, you can have a single-story panel with a punched window opening or a double-story panel with 2 punched window openings. And the same facade fenestration can have spandrel panels with column covers and achieve essentially the same window opening pattern, but as you can see, the facade looks completely different whether you have spandrel and column covers or whether you do T-shaped panels. So there are a whole host of things that can influence how the panels are supported on the base building structure. In terms of accommodating movement, when the gravity load of the panels is supported by the spandrel beam, we need to make sure that the horizontal soft joints between panels, as we see here, this is a vertical cross section between 2 panels, we need to make sure that horizontal soft joint can accommodate movements due to the relative deflection of the upper and lower floors, and can accommodate temperature changes in the panel due to ambient conditions, and can also accommodate shrinkage of the panel, particularly for a precast panel. We also need to be sure that we're accommodating lateral changes due to volume. So you're going to get some shear along this joint parallel to the plane of the wall. You'll also get some shearing of this joint due to in-plane story drift. And you may get some compression or extension of these joints due to out-of-plane loads due to wind and seismic forces. When it comes to lateral forces, and this is particularly true for precast panels, which are relatively heavy, the panelized facades can impose some fairly substantial seismic forces on the base building frame, forces that need to be considered in the design of the beams and columns that support the panels. So take, for example, a precast concrete panel where the center of mass of the panel is well above the gravity supports, which are shown down here with this pin and this roller. When this panel undergoes an in-plane seismic force, it's going to cause overturning because its seismic force is at the center of mass of the panel and its resistance is at the corners. And so that overturning force has to be split into a couple between the two gravity supports, and that needs to get added to the gravity reactions from the panel's dead load. For out-of-plane loads, the panel tends to flex like a simple beam between the lateral connections at the top and bottoms of the panels. In terms of field adjustability, it's generally recommended that the slab edge be adjustable perpendicular to the plane of the panel itself, just as with the masonry veneer. But this is particularly true for panelized facade systems, where we need to provide some clearance to accommodate field and erection tolerances, and also the fact that there may be some sweep in the panel itself. The panel is likely not to be perfectly flat. So we need to provide a gap between those. Often it's 2, 2.5, or maybe 3 inches. And the durability of the connections here is particularly important as well, because as I mentioned before, the panel is a barrier wall system, and depending upon the sealant joints between the panels. If the sealant joints leak and these connections are exposed to moisture, we may have a durability problem and not realize it. And so for that reason, the connections of the panel to the building structure need to be fairly robust. Here are some examples of how vertical adjustability is accommodated through the connection, and these would all be designed by the specialty structural engineer working for the precast or panel manufacturer. Here you see we're providing some shims between an embed plate cast into the top of the slab. Those shims can be increased or decreased as necessary to get the panel plumb and square. Alternatively, you can use something connected to the back of the panel with a leveling bolt, which allows the panel to be plumbed and squared. As I mentioned in the previous slide, we have a fairly wide gap between the slab edge and the back of the panel, and that needs to be filled with a fire-safing material to prevent flame and hot gas from traveling from one floor to an adjacent floor in the event of a fire. Let's talk about some connection types. And before we get started with that, I think it's really important that the panel manufacturer be involved as early in the design process as possible, because it's the fabricator who's ultimately responsible for the design of the connections to the base building structure. And that specialty structural engineer working for the panel manufacturer needs to collaborate with the structural engineer, so the structural engineer record for the base building structure understands which types of panel connections are to be used and where they'll be located and the magnitudes and directions of the forces that are imposed on the base building structure. So there are a variety of ways to support gravity load or bearing of the panels in the base building structure. And again, these will be designed by the specialty structural engineer working for the panel manufacturer. Again, we're showing precast here, but these could just as easily be any of the panelized systems that I mentioned in the first slide of this section. So let's look at some of these in a bit more depth. Actually, let's back up to this one for just a second. Here you see a panel that's bearing on a bracket directly on a column. This panel would span from floor to floor and also span from column to column. In the middle image, you see a panel with a fairly rigid bracket bearing on an embed in the top surface of the slab. And in the image on the right, you see a fairly rigid bracket connected to the back side of the panel in a blockout or recess that's created in the slab, and then this recess would be infilled later with concrete. So those are some of the bearing type connections. In terms of lateral connections, those are connections that restrain only out of plane load. It's typically done through a rod or some relatively flexible element that is good in tension and maybe compression, but not particularly rigid for in-plane motion. So that's what you see here. This is a lateral type connection connected to the top flange of a spandrel beam. It's also possible to do a relatively flexible connection to a column as well, as you see here. Here are some types of tieback connections that are for relatively limited access spaces where it may not be possible to attach to the top or bottom flange of the spandrel beam. And you also need to have alignment connections between adjacent panels to prevent them from displacing out of plane with respect to one another. And those, again, will accommodate some adjustability through slotted holes, or in some cases through the use of field-welded connections, as you see here. So digging into some of the bearing type connections a little bit further, here again you see a panel that's bearing on a bracket on the base building structure column. So the bracket in this case would be designed by the specialty structural engineer, and the panel would bear on that bracket and be field welded to it. In this case, it's a story tall panel. It spans from floor to floor and also spans horizontally between adjacent columns. Now, this is going to be a very efficient system in that the load is transmitted from the panel directly to the column, and the spandrel beam isn't penalized by having to take any gravity load from the panel. But the thing to remember here is you are imposing a fairly significant moment on the column, and depending upon how the column is oriented, whether it's in strong axis or weak axis condition, that can be a very significant moment for the column to have to resist. Typically, this is done at the floor level so that this connection to the floor beam behind here could conceivably be moment connected or designed to resist some moment associated with the bracket. In the case of the spandrel-supported panel, as you see here, we are providing a block out in the slab, which will get filled later after the panel is erected. And that needs to be carefully coordinated with the concrete subcontractor responsible for placing the flat work. And the spandrel beam itself needs to be designed to take that gravity load and deal with the eccentricity of the panel, this value EF. In addition, there are lateral forces from the panel below, which are resisted through this hanger and this kicker. We have to consider in our design. And it's important, although these connections will be designed by the specialty structural engineer working for the panel manufacturer, the structural engineer of record needs to understand what the magnitudes of those forces are and how they're applied. In some cases, at the top of a building, it may still be advantageous to hang a panel, like you see here, from the roof spandrel beam. But be aware that in this case, you have fairly significant out-of-plane load on the bottom flange of the beam through this lateral tieback. And we can resist that through a kicker, as we're showing here, but where does the horizontal component of this kicker go? Well, in this case, we're providing a strut to take out that horizontal load and drag it into the roof diaphragm. It may also be possible to put this angle on top of the roof deck to help drag that load into the roof diaphragm. So there are a few potential problems to consider when you're designing a panelized facade system. First is that the erection sequence may be very complicated and it will require coordinating brackets, embeds, blockouts, or recesses in embed plates, and inevitably some of these get missed. I'm dealing with a project right now where that is the case, and it's a real struggle on a daily basis. We also need to consider the fact that the brackets will cantilever on the back side of the panel, and they may not have sufficient stiffness and may allow the panels to rotate significantly during deflection. And we also need to consider what the division of the responsibilities for designing and providing the attachments is. Who's responsible for showing what? And what I recommend is that the structural engineer of record and architect show on their drawings what they are specifically responsible for, and what they're delegating to the specialty structural engineer working for the panel designer and panel manufacturer. So that's clear, and that there's a clear understanding of the loads that have to be resisted by the base building structure and where those loads are applied. We may also have a case where joints in the architectural panelization are not well coordinated with points of load application to the primary building structure. And so that really behooves the structural engineer of record to pay close attention to the architect's wall elevations, and also look at the panel manufacturer's shop drawings to understand how those are supported. We also need to make sure there's adequate coordination and accommodation for adjustability by both the structural engineer of record and the specialty structural engineer. We need to make sure that we know where the slab edge is going to be, and that we provide adjustability for it, and that the brackets that are on the back of the panel, whatever those are, can accommodate some adjustability as well. We also need to make sure that the specialty structural engineer's attachments deliver moments and forces to the primary building structure in a way that are anticipated by the structural engineer of record's design of the base building structure. We also need to make sure that we resolve horizontal and vertical kicker loads at lightweight roof structures, and that we're cognizant of how loads are applied to the bottom flanges of spandrel beams, and that as the structural engineer of record, we understand those loads and how they're resisted. So that's the end of our portion on panelized facade systems. Let's move on to aluminum glass curtain walls. There are a variety of different aluminum glass curtain wall types that are on the market these days, and in general, there are two basic kinds, and they're hybrids of those. The first of them is a stick-built system in which the mullions are brought to the site and erected first, and the panels of glazing or spandrel panels or maybe even metal panels set in the curtain wall system are erected after the mullions are in place. So we call this a stick-built system. You can also have panelized facade curtain wall systems in which mullions and glazing and spandrel panels are prefabricated in the manufacturer's shop, brought to the site, and erected as panels. And you can have hybrids of these systems as well, with stick-erected mullions and panels that drop into those stick-built mullions in the field. Let's talk about some strategies for support of curtain wall systems. The first and foremost thing is that they are easily accessible. We need to make sure that the curtain wall erector is able to get to the connections and make them easily. We need to accommodate for adjustability, as we do in all of these with our slab edges. And that may mean that if we're providing a attachment to the slab edge itself, that we provide a bent plate pour stop, and that bent plate pour stop needs to be adjustable. We need to try to work to minimize the eccentricity between where the curtain wall is supported on the base building structure and where the load is applied. And since spray-on fireproofing is often applied prior to the installation of the curtain wall system, blockouts need to be provided in that fireproofing and patched after the anchors are installed. We also need to think about the fact that erectors often prefer field-welded connections over bolted connections, since they allow for greater adjustability, but that may be challenging if you're working in a building in which field welding is limited. Just as with panelized facades, there are two essential connection types to the base building structure. One is a dead and lateral attachment, which you see here in the top portion of the slide. And that allows that resists gravity loads as well as out-of-plane loads. And then there's a lateral-only attachment, which you see in the lower portion of this slide. This resists only wind and seismic loads out of plane of the curtain wall. And you would have this type of connection where you have a multi-story curtain wall, where you have multiple vertical spans of the curtain wall mullions. So some architectural parameters that affect the design are the locations of the mullions in plan, the locations of the horizontal joints in the mullions, that is to say the joints that accommodate thermal changes in the aluminum mullions, as well as deflection of the base building structure, what type of system is, whether it's stick-built or panelized, the story height, which again will influence the widths of the sealant joints between the curtain wall sections, what's aesthetically acceptable in terms of mullion size, and the direction of the span. In buildings with multi-story atria, for example, where you don't have a floor level directly behind the curtain wall, you may need to provide some horizontal structural steel girts that would laterally support the curtain wall at every floor level if you don't happen to have a floor level where you need to provide lateral support for the mullions. Accommodating thermal movements in curtain wall systems is really critical. It's a very important part of the curtain wall design itself. Aluminum expands about roughly twice the rate of the structural steel framing or the concrete framing, and this is a real phenomenon and needs to be accommodated in horizontal joints within the mullions. And typically it's the specialty structural engineer responsible for the curtain wall design who will provide the details for accommodating the thermal movements in the mullions. But that needs to be done collaboratively with the structural engineer of record who knows how much the base building structure spandrel beams are going to deflect. In terms of accommodating structural movements, typically curtain wall is designed for an out-of-plane deflection of about span over 175, unless it's supporting brittle finishes also, in which case you might need to restrict it to the vertical span over 360. But we typically put a maximum cap of about 3/4 of an inch out of plane when we're designing elements that support curtain wall out of plane. In plane, there is no magic number, but typically it's about span over 360 with a 3/4 inch maximum. But I've dealt with projects recently which have had about a 3/8 of an inch maximum structural deflection to try to minimize the widths of the sealant joints between curtain wall sections. Just as with panelized facades, there are gravity or dead load anchors, and there are lateral anchors. Gravity anchors resist not only gravity load, but lateral load. And here's an example of a gravity load anchor. This is a clip which was provided by the curtain wall manufacturer, which is field welded, in this case, to a bent plate. This could be a pour stop, or maybe it's at the roof level. That's field welded for adjustability. And there's an erection fastener, which is probably a self-drilling screw placed through the aluminum mullion. And once that location is set, the structural fasteners are installed. And then the erection fastener may be abandoned in place or it may be removed. What's important here is that this connection does support both gravity loads as well as out-of-plane wind and seismic loads. In a multi-story curtain wall, you will also have lateral anchors that are capable of resisting just out-of-plane wind loads. It looks very similar to the anchor for dead load I just showed you, except that we've provided vertical slotted holes in the clip. And once the location of this is finalized and the structural fasteners are installed, the erection fastener is removed, and this allows the mullion to displace vertically a small amount with respect to the spandrel beam. Now, how do you support the curtain wall manufacturer's clips on the base building structure? One way to do it is to provide a bent plate or some sort of downturned angle, particularly if you can't accommodate attachments on the top side of the slab. In this case, the curtain wall mullion clips might be field welded to this downturned plate. Maybe you need to put in a full depth stiffener if this is a particularly long slab edge. That's one way to do it. Another way to connect the curtain wall to the base building structure is to provide a connection down here to the bottom, near the bottom flange. And again, you might need a stiffener to account for local bending forces. But again, the clips from the manufacturer be welded to this bent plate or this angle. Here's another example where the curtain wall manufacturer and erector connect the mullions directly to the spandrel beam web, and they provide all the hardware to do so. So the red angle that you see here would be field welded, temporarily bolted, but ultimately field welded to the spandrel beam web. And the connection plate back here bolts to this, and that in turn gets bolted to a receiver channel that is attached to the aluminum curtain wall mullion. And here's another example of a curtain wall detail where we attach to the top surface of the slab. So these connections can now be made from within the building rather than having to work from outside the building before the glazing is in place. So this may be a common type of application for a unitized curtain wall that is pre-glazed. In that case, we've cast a plate into the top surface of the slab, and the manufacturer's angles are field welded to that embed plate, and then there is another plate that gets attached to the angle, and that's attached to the curtain wall mullions. Again, notice the detail provides both vertical and horizontal adjustment using the slotted holes here. And everything that is red or blue would be provided by the curtain wall manufacturer or erector. Now, sometimes it's not possible to have hardware that sticks up above the top surface of the slab. In that case, it may be necessary to do a recessed anchor where there's a block out in the top surface of the slab that allows the curtain wall to get attached to the top edge of the slab from within inside the building, and these pockets would then get infilled later with grout once the curtain wall is erected. Also notice here that this connection is allowing for vertical movement. This is a mandrel type connection where the outer curtain wall mullion slips over the top of the lower male connection, and that allows the curtain wall above to displace vertically with respect to the curtain wall below. So this is a kind of a movement anchor. Another example for attaching to the top surface of the slab is to cast in an embedded angle and weld directly to that. And again, this is also a mandrel type connection where the upper mullion section slips over the male end of the mullion below. So there are some potential problems with curtain wall systems, as with any system. Large gaps between the anchors and the primary building structure can result in excessive bending stresses in the curtain wall supplier's hardware. We can also have problems with the coordination of locations for adjustment and specifying and understanding who is going to be able to adjust what when things are in the field. We need to make sure we provide slotted holes that are long enough to accommodate variability in the top surface of the slab or the planned location of a spandrel beam that we're connecting to. We need to make sure the bolted attachments are coordinated with the primary building structure, and if any bolt holes need to be drilled in the shop, that those are done. And that mullion splices properly account for volume changes due to temperature during the life of the building. So that's it for aluminum curtain wall systems. We're going to move on to talking about vertical movement joints that occur between masonry veneer or between panels or between curtain wall sections. And it's important that we consider the fact that the facade joints are building components just like any other component of the building. They need to be explicitly designed and not just winged at the last minute right before the CDs go out. So we need to think about how these joints accommodate movement, how they deal with sealant failure, how they deal with air infiltration, how they deal with water leakage. So some fundamentals of joints are that every facade system needs them. There's no escaping them. And they need to accommodate movements due to building structural deflections as well as thermal changes in the facade and moisture changes in the facade in the case of masonry veneers. And they need to be able to accommodate tolerances as well. This is where the tolerances may be able to be made up in the erection of the steel frame. In some facade systems, particularly barrier wall systems like a precast panel system, the joints also control air and water into the building, and performance of those sealant joints is critical to the air and water tightness of the building. So what types of movements do we need to accommodate in the facade joints? Well, they're dead loads, superimposed dead loads, they're live loads and rain and snow loads just like any other structural component, as well as wind load and seismic loads. But what's particular to facade joints that we need to think about are long-term shrinkage, particularly in concrete buildings in which columns will shrink over time, or spandrel beams may undergo creep deflection over time. We need to think about differential settlement of the foundations and how that may affect the facade. Thermal movements, as we've been talking about, and moisture-related movements of the facade materials themselves. So what movements do we actually need to consider when we design the horizontal joints in the facade? Well, we're really interested in the movements that the joint experiences during and after the facade's installation. So we do not need to consider the self-weight deflections of the spandrel beam, and that includes the self-weight of the concrete slabs in the building. We may not need to consider the superimposed dead loads on the building, particularly if it's a large piece of equipment that's installed long before the facade is attached to the building. We might need to consider the superstructural movements due to the facade installation itself, depending upon what type of facade it is and when the sealant joints will be installed. We certainly need to consider any live load, rain load, snow load, or seismic movements that the building undergoes, as well as long-term shrinkage of any components of the building structure, as well as differential settlement. So those have to be considered in the width of the joint and sizing of the movement in the joint. And in addition, we need to consider the thermal movements and the moisture movements. Those have to be considered in the design of the joint. A quick word about spandrel beam related movements, and we'll cover more of this in subsequent sessions. Consider the fact that the spandrel beam is eccentric to where the facade load is applied, and that facade load induces not only direct vertical deflection of the spandrel beam, but also rotations, as we've been talking about, as we show here on the right. And that rotation of the spandrel beam results in an additional vertical deflection. So this is vertical deflection due to rotation, not just flexure of the spandrel beam. The rotation of the spandrel beam also causes a horizontal translation of the locations where the facade is supported, particularly in the case of a hung masonry shelf angle. We also need to think about how vertical movements are going to affect vertical joints, between the panels. So for example, in the case of the spandrel beam above, I'm obviously showing a grossly deformed spandrel beam here, but as that spandrel beam deflects, the vertical joints at the bottoms of the panels will tend to open, and the joints at the tops of the panels will tend to compress. We need to make sure we're accommodating vertical deflection of the spandrel beam as that affects the widths of the vertical joints of the building. There are some pinch points for vertical joints, and those are particularly between unloaded and loaded floors. So for example, this floor up here is unloaded and the floor below it is loaded, and so the joint here tends to open. In comparison, if this floor is loaded and the one below it is unloaded, we tend to get compression in this joint. And this tends to happen at floor levels immediately below the roof, and also the first elevated floor level above the foundation of the building. One thing we need to consider, particularly in very tall buildings, is column shortening. For a relatively low-rise building, 5 or 6 or 7 stories, it may not be a big consideration, but as you're building a very tall building, the columns will compress as the upper floor levels are installed in the building. And if you've installed sealant joints in the facade in the lower floors, and you're continuing to place floors in the upper levels of the building, you may be compressing those joints more than they can accommodate. So it's something to keep in mind for very tall buildings. Differential settlement of the foundations is a real concern when you're looking at facade systems. We need to anticipate foundation differential settlement, and that needs to be accommodated through the vertical joints in the facade. We also need to think about thermal movements in the facade as well. Typically, the interior of the building is conditioned. It's maintained at a constant temperature day and night, whereas the outside of the building undergoes fairly wide temperature swings, particularly from winter to summer or from morning to night, depending on whether the sun is impacting the facade directly. And that can cause out-of-plane deflection of the facade system as well, as we'll talk about in an upcoming slide. So thermal changes are really a function of the facade's coefficient of thermal expansion, and that's a function, and the amount of movement you ultimately get is a function of the temperature change from when the facade system is initially installed, and the length of the member between horizontal joints and the coefficient of linear expansion. As I mentioned before, in the previous slide, when the interior of the building is held at a relatively constant temperature and the outside is subject to fairly wide temperature swings, you may find that the exterior cladding undergoes bowing out of plane as the vertical displacement is restrained, and the facade system has to do something to accommodate its change in temperature, and it does that by bowing outward or maybe bowing inward, depending upon the temperature swing. As I've been mentioning, particularly for masonry veneers, we need to accommodate facade moisture movements. This is most prevalent in stone and brick masonry, and brick masonry in particular undergoes irreversible growth due to water absorption by as much as 0.2 to 0.07%. The joint material, which typically the structural engineer doesn't have much control over, is also an important consideration in the joint design itself. We are often seeing modern sealants capable of displacing or compressing up to 50% of the original joint size, but not all sealant joints are capable of doing that. And so it's really incumbent upon the design team to confirm with the product manufacturer just how much the joint sealant can be compressed or stretched. One solution I'm seeing in a lot of buildings these days is to leave the joint open to sealant and provide an extruded silicone sheet behind that is really the waterproofing barrier. And these are capable of much more stretch as well as compression and can allow for smaller joint widths than a conventional sealant joint. Here's an example from a project that I've worked on recently. These have fairly wide horizontal mullions in the curtain wall that you see here, circled in red. And here's what a cross-section of that looks like. We're providing a membrane joint between the two portions of the curtain wall that allow this joint to effectively compress to almost nothing. In terms of the load combinations to consider when designing the joints, the building codes provide some guidance on load combinations, but no specific requirements. Serviceability checks, for example, compression of a sealant joint, probably allow you to use a lower force and probably a lower wind or seismic drift when considering the joint sealant movements. And so ASCE 716 commentary provides a list load combination, which is dead plus half of live plus wind A, and wind A is the wind that occurs at reduced wind speed that is associated with a lower return period. So in terms of decising the joints themselves, this equation is published in a number of places, including AISC's Design Guide 22, and it's for determining the width of a sealant joint based on thermal, moisture, and structural deflections and tolerances and the joint compressibility. So this is specific to sealant joints here. In this expression, J prime is the width of the joint before filling the joint with the sealant. Alpha delta TH is the thermal movement. KEH is the moisture movement. Delta SIL is the superimposed deflection that occurs after the sealant is in the joint. M is the compressibility of the sealant. Tol is some tolerance that's built into the connection. I'd recommend at least 1/8 of an inch from where you think the joint's going to be. And delta PS is the deflection that occurs prior to the sealant being installed in the joint. So that might be the deflection of the brick on a shelf angle prior to installing the sealant. So we're going to run through a quick design example here that's in Design Guide 22, example 7.1. We're going to look at a clay brick veneer building, which is supported on the base building structure by a shelf angle at each floor level, and we're going to try to compute the amount by which the spandrel beam can deflect before compressing the joint filler material beyond its maximum allowable compressibility. In other words, we're trying to set what the deflection of the spandrel beam is due to all the loads that occur after the sealant is applied to the joint. Here's a cross-section of that joint, brick masonry veneer, shelf angle, backer rod, and elastomeric sealant, and its original width after the sealant is installed in the joint is J, or J prime before the sealant is installed in the joint. So again, here's the statement of the problem. We're looking at a 14-foot story height. We're going to provide a tolerance of 1/8 of an inch. We're going to have the shelf angle limited to a deflection of 1/16 of an inch. We're going to look at a temperature swing of 100 degrees from when the brick is installed. we're going to look at a expansion coefficient of 4 times 10 to the negative 6 inches per inch per degree Fahrenheit, and this moisture coefficient for the brick. And we're going to assume that the initial joint width before sealant is installed is 7/8 of an inch, and that the compressibility of the sealant material is 50%, which is consistent with a high-performance sealant. So here again are those terms fleshed out for you. And we're going to use the expression that we showed you in the previous slide, where J prime is the width of the joint before sealant is installed in the joint. J is the finished joint width. This is the tolerance, and this is the deflection, delta PS, that occurs prior to the sealant being installed in the joint. So that would be the deflection that occurs after the beam, let's say, is a composite beam. That's the post-composite deflection due to, say, the brick veneer going on the building. We can break that down into a number of subcomponents. This is the thermal movement, the moisture movement, post-composite superimposed deflection after the sealant is installed. This is the compressibility of the sealant. And we can rearrange this to be in terms of deflections and in terms of movements. So delta S we're going to define as superimposed deflection after the sealant is installed times the compressibility of the sealant times the pre-sealant deflections. And delta VB is the change in brick growth due to moisture and temperature. So I won't run through all the calculations here. You can do that as we're running a bit short on time. But first thing to note is that this term delta JM, that's the compressibility of the sealant times the quantity original joint minus the tolerance. So right out of the gate, we're going to deduct 1/8 of an inch off of the initial joint width for tolerance, and we're going to multiply that by half. So this joint can move at most 3/8 of an inch before the sealant is overcompressed. We need to subtract off the brick growth from that, and that leaves us with structural displacement of 0.257 inches, which is pretty tiny, particularly if I've got long span between my columns. And working through the algebra here, we ultimately find through using the ratio of the loads on the spandrel beam to their deflections that we end up with a superimposed deflection of just about 0.15 inches. That's the amount that the spandrel beam can deflect once the sealant is installed in the joint, considering the brick growth, due to moisture, considering the brick growth due to thermal, and that's what's left over for the structure to deflect, which is not very much, considering that we started out with a 7/8 inch joint. Now, when you're working in your calculation software trying to determine what the deflections of the spandrel beams should be limited to, it may be difficult or cumbersome to try to decouple brick deflections from superimposed deflections that occur after the sealant is installed in the joint. So it is conservative to set delta S equal to delta PS plus SIL, which is the total deflection of the spandrel beam after the beam is composite. A quick word before we wrap up on the effects of vertical movement on vertical joints. Again, as the spandrel beam deflects, we need to be sure we're accommodating the joint opening up between adjacent floors or compressing between adjacent floors, as we show here. And in addition, that vertical deflection of the spandrel beam causes vertical joints to undergo compression at the top and expansion at the bottom. And so with that, my final slide, talking about effects of horizontal movement on joints. And just be aware that the horizontal displacement between floors due to wind and seismic forces causes shearing in these joints and may also cause racking of the panels themselves. And so with that, I'll turn it back over to Nate for some questions.
All right. Thank you, Alec. We have a number of questions from the audience, but first we're going to start with a couple of questions for the audience in the form of polling questions. And so here is our first polling question, a multiple choice question, which the audience can select the answer that they think is best on their computer screen. So the question is as follows: which of the following is not typically a panelized facade system? Is that A, full bed stone veneer, B, thin stone veneer, C, panelized brick on metal studs, or is it D, glass fiber reinforced concrete? And the question is, which of the following is not typically a panelized facade system? Select that answer on your computer screen. We'll give it just a little bit of time here for everybody to get their answers in, but their answers are coming in here. Go ahead and close the poll. All right, so Alec, it appears that 82% of our audience thinks the answer is A to this question. Did they get that right?
Yes, I would agree with that. The answer we were going for was full bed stone veneer, which is typically laid by masons in the field using mortar beds. The other three systems are quite often panelized on a truss that's fabricated maybe of structural steel or maybe light gauge metal framing that is then hung on the building.
All right, good job, everyone. We'll try you with one more question, polling question. Follows. Which of the following does not need to be considered in sizing joints for vertical movement? Is that A, live load deflections, B, seismic drift, C, differential settlement, or is it D, building self-weight deflections? Again, which of the following does not need to be considered in sizing joints for vertical movement? Right, so looks like most of the answers have come through here. Alec, we'll go ahead and close the poll. All right, so it looks like about 64% think that that answer is D. We do have about 28% who thinks that answer is B, seismic drift. So which one is the correct answer we're looking for here, Alex?
So the answer we were going for, Nate, was building self-weight deflections. And the reason for that is that the building will have deflected under its own self-load that includes the weight of the steel framing and the concrete slabs on deck long before the sealant is applied to the joint. What we really need to do when we size the joint is be able to accommodate how much movement the joint can accommodate, how much it can compress or expand. The seismic drift is I think people are maybe thinking about this in terms of vertical movement of the joint, but also think about the fact that as the building undergoes lateral drift, one floor is going to have to displace relative to the floors above it and below it. And those joints are going to be sheared parallel to the plane of the joint. So we do need to consider that in the design of the sealant materials.
All right. Well, now let's go ahead and move on to some questions that has come in from the audience. And the first question will bring us to slide 15. And the question is on this discussion on masonry cavity walls. In general, are these joints that you're discussing here, the vertical and horizontal joints, are these joints visible from the outside of the building?
Yes, they are. They are visible from the outside of the building. Typically I've found that most architects, particularly in the masonry cavity wall, particularly for brick, where the mortar beds are on the order of 3/8 of an inch between masonry courses, most of my architectural clients strive for a 3/8 inch wide sealant joint, which can lead to a very tight deflection criteria for the spandrel beams. The vertical joint widths can vary, but they're typically about the same width, maybe a little bit wider. And typically those get spaced about 25 feet on center, but again, that's something the architect would typically be responsible for specifying. But yes, these are visible from the outside of the building. And sometimes they're color matched to the mortar, and sometimes they're not. Okay.
Moving on, this question was asked at about slide 25. Pull that up. Question is again on these masonry cavity walls, does the creep of the masonry ever become a detailing issue?
Well, that's a good question. I think when I think of creep, I think of usually in terms of compression of a section and increasing amounts of deflection due to a sustained dead load or a sustained applied load. Usually I'm not seeing that so much in the masonry. I mean, what I do see as an issue is the moisture growth of the brick over time as the brick masonry absorbs moisture from the environment and grows. We have seen cases where that happens over time, and that does over-compress the sealant in the joint and cause it to bulge.
All right. Moving to slide 36, a couple questions on this detail. A couple of people asked, what is the isolation pad material here? And there's another follow-up question, is there ever concern about crushing of the isolation pad?
So those are both two good questions. I won't endorse a particular product that we used here, but I can tell you that it's a fiber-reinforced plastic product. Crushing of it is a concern, and so you do have to consider keeping the stresses on the compression on the pad to about 1/5 or so of the ultimate compression strength of the material. In addition, due to the compression of that material, you will get additional rotation of the shelf angle as the pad compresses that you need to consider. So imagining the hardware to the left of the thermal isolation pad rotating as a rigid body about the bottom right-hand corner of that assembly, compressing the pad. So you do get additional rotation out of it as well.
Slide 48. The question on this detail was as follows. Can the shelf angle be bolted to a preset anchor as an alternative to this detail?
Bolted to a preset anchor. I'm not sure I understand the question, Nate. I think the question is, can it be bolted to a headed stud or something like that that extends through the bent plate?
Yeah, I think a preset anchor attached to the bent plate, or I suppose embedded in a concrete slab potentially as well.
Yeah, I suppose in theory that it could. You could use something like a welded stud welded to the vertical outside face of the bent plate, but be aware that if you do that, you may have difficulty with shimming where the horizontal leg ends up. You're going to need to be able to provide some adjustability, and that's why it's typically done with welded steel shims. I suppose it could be done. I have never done it myself.
Okay, I'm going to jump forward in the presentation to slide 90. Question came up during the discussion on aluminum curtain wall systems. What kind of connection from aluminum mullions to the structure should be used to take into account any galvanic coupling? So, you know, for example, stainless steel or galvanized type anchors?
So sometimes you actually provide a electrical insulator between the aluminum shoe and the steel plates. I've seen that done sometimes, or maybe it's done with a coating on the two. But it really only comes into play if you have moisture in the connection, and this is behind the moisture barrier, so it's usually not a big concern, but sometimes you do provide a coating or effectively a bushing between the two to isolate them electrically.
Right, so we're actually a little bit past time, and so we're going to go ahead and end the live question and answer portion for today. But I do want to let everybody know that we we have received your questions even if we didn't happen to get to them in the time allotted. And we'll work with Alec to respond to those individuals whose questions did not get answered. We'll try to provide some responses via email working with our speaker. So a few announcements before we break for today. So once again, I want to remind people how they can get their PDHs. So for the single session registrants, and that means you only register for this specific session on this particular registration, and you'll be seeking PDHs for multiple people at your connection. Remember that within 2 business days of today's session, you'll receive an email with information on how to report attendance. You'll be getting that from the address on your screen, registration@aisc.org. That email will contain a link to an online form, and you can fill out that form to report attendance for you and everyone at your connection. And PDH certificates are then sent out via email to the individuals that attended. For those of you that register for the 4-session package, remember that you will be receiving PDH credit at the end of the entire course, so after all of the sessions have been presented. PDH credit will be awarded for each session based either on your attendance of the live session or based on your viewing of the session video recording and passing an associated quiz. The video and the quiz for session R1 was available to you as soon as you registered for the 4-session course. And then the video and quiz for each of the 3 live sessions will be available by the end of the day on Friday, the day after each respective live session. And you'll be getting an email reminding you of the quiz and video availability from webinars@aisc.org. Note that all videos and recordings are available until Monday, June 17th, and that is the date that represents the end of the course. And certificates will be sent out to 4-session registrants that week of June 17th. 4-session registrants can find all of their handouts, quizzes, quiz scores, recording access, and attendance information on the website. Just sign in at aisc.org and go to your profile and then select course resources. And you can select the course you're in and you get a screen that looks like this with all the course information in one place. Also, before we break, I do want to make you aware of our summer night school course. That's Classical Methods of Analysis, presented by Dr. Lou Geschwindner. That course is now open for registration. In this course, you'll see how understanding classical methods can enhance your understanding of modern design and analysis requirements. Our night school is an 8-session course held on Monday evenings. Class begins on June 3rd. So to learn more or to register, visit the webpage on your screen, aisc.org/nightschool20. In a moment, this session is officially going to end, and a survey will pop up on your screen. Please help us out by completing our survey form. It's very short but very helpful to us in improving this continuing education programming for you. Thanks to Alec Zimmer for presenting the first live session today, and thank you all for your participation. Enjoy the rest of your week, and we'll see you next week for session L2 of this AISC webinar series.